Hello again. We are studying Chapter 9, Introduction to Differential Equations, and we're on the topic of separable differential equations. So we're going to go over a couple of examples here. Remember what the process is to solve a separable differential equation is we want to separate the variables in our equation, isolating one variable on one side of the equation and isolating the other variable on the other side, keeping in mind that our notation for a derivative here, such as the one that you're looking at here, dp dt, I can tell this is a differential equation because it contains an equation that has a derivative and its function. And the function that we are trying to solve for is p, because dp dt, that is the derivative of the function p with respect to t. So if we're going to separate our variables p and t, we want to make sure, because the last part of our process is to integrate both sides. And if we have an integral f of x dx, for example, notice that our differential dx is a factor that is multiplied, or in other words, it's in the numerator. So my first step here in separating the variables, if I see dp dt, is I'm going to multiply on both sides by dt. So I get dp equal to t squared p minus p plus t squared minus 1 times dt. Now this one looks like a little tricky to separate the variables because it looks like p's and t's are everywhere. But if we go back to factor by grouping, then we probably will get somewhere. So if I begin just grouping the terms, I'll group the first two terms together, and I will group the last two terms together. And now I'm going to factor out what I can using the distributive property. And I end up with, in that first one, I can factor out a p, and I'm left with t squared minus 1. And in the second grouped terms, I can't factor any common factor, so the actual common factor is 1. And now I see a common factor among the two terms here of t squared minus 1, and so I'm going to factor that out. And I end up with t squared minus 1 times, and what's left over from the distributive property is p plus 1. And now I can divide both sides by p plus 1, and I end up with dp over p plus 1 equal to t squared minus 1 dt, variables separated. And our next step in solving is to take the integral of both sides, and that's why we want to have our differentials in the numerator. On the left-hand side, we would use a simple u substitution of p plus 1, and so hopefully we see that this turns out to be the ln of p plus 1. And on the right-hand side, I can integrate directly, and I get t cubed over 3 minus t, and I could have put a plus c on this side, which I should, and then I'll also put a plus c on this side, but they're arbitrary constants, and I could move the other c and combine them, so I don't really need to, on the left side, add a plus c. Just make sure that you introduce a plus c on the right-hand side so that you have in your general solution a family of functions. So this is our general solution here. Because it is a family of functions. If you want, you can solve for p. This is also a general solution in implicit form. If you want to do an explicit form, then we want to solve for p. Right, and p should be a function of t, right? So if we solve for p, then we would have to exponentiate on both sides, and we would get e to the ln of p plus 1 equal to e to the t cubed over 3 minus t plus c. And I can rewrite this as e to the t cubed over 3 minus t times e to the c. And I can use this e to an arbitrary constant, can be my new c. My new arbitrary constant. And so in simplifying this expression, we would get e to the ln of p plus 1 is p plus 1. And then we would have e to the t cubed divided by 3 minus t times c. And we'd put that in the front. And then finally solving for p, we would get p equal to c times e to the t cubed over 3 minus t minus 1. And that would be the solution, the explicit solution of this differential equation. Good. All right, so now let's move forward to some initial value problems. So here we have, instead of finding just the general solution, they're going to ask you for a particular solution, namely which one is going to satisfy y is equal to 1 when x is equal to 1. These are what's known as our initial values. Good. So first, let's separate our variables. And I see dy dx equal to negative xy squared. So I'm going to first move the dx to the right-hand side by multiplying, and I would get dy equal to negative xy squared times dx. And that prompts me to divide both sides by y squared to separate the variables. And I get dy over y squared equal to negative x dx. And now I'm going to integrate both sides. And in integrating both sides, I'm going to transform the dy over y squared to a negative exponent. And I get minus x dx. Now I'm going to integrate both sides, and I get minus 1, or y to the minus 1 over minus 1 equal to negative x squared over 2. And don't forget your plus c. And this is, and just simplifying things, this would end up being minus 1 over y equal to negative x squared over 2 plus c. This is the general solution. And that is in implicit form, because we have not solved for y being the solution to the equation. I tend to leave it in implicit form when I go to find the particular solutions. So here I go, finding the initial, using the initial values. So if I use my initial values, to find the particular solution. So we have y is equal to 1 at x equal to 1, and I'm going to use the general solution here, and I have minus 1 over equal to minus squared over 2 plus c, and I'm going to substitute my y is equal to 1 and my x is equal to 1. And so in simplifying this, I get negative 1 equal to negative 1/2 plus c, and I can move the plus 1/2 minus 1/2, or sorry, minus 1 plus 1/2 is equal to c, and I would get that c is equal to minus 1/2. So my particular solution is going to be the general solution, minus 1 over y equal to negative x squared over 2, but now I'm going to replace the c with minus 1/2. I can now, after I've found my plus c, it might be easier to find the explicit form by solving for y. So this minus x squared over 2 minus 1/2, that does equal minus x squared minus 1 over 2. And so and that also equals minus x squared plus 1 over 2. So in just coming over here, I have the minus 1 over y equal to minus x squared plus 1 over 2. And I can take away the negatives, but also take the reciprocal. And so I end up with y equal to 2 over x squared plus 1. And that is my particular solution in explicit form. Good. All right. So I'm going to skip ahead and let's do one involving e to the minus z. And this one is through the point 0, 1, and this is our point. This is our initial value of, notice here that this is dz dp, and it's kind of like the dy dx. And so we know that what's on the denominator is going to be our input value, and our output value is going to be z. So this translates to p is equal to 0 and z is equal to 1, and these are our initial values. Good. All right. So let's do this. We want to separate our variables, and we see that first, if I do dz equal to e to the negative z dp, it prompts me to move the e to the negative z over to the other side. And before we go to integrate, I'm going to transform the left-hand side by moving the negative exponent up to the numerator. And now I'm going to take the integral of both sides. So the integral of e to the z dz should be equal to the integral of dp. And the integral of e to the z is e to the z. And the integral of dp is p. Good, plus c. That's my general solution in explicit form, or implicit form. And now I'm going to use my initial values to find the particular solution. Good. And so I'm going to plug in e to the first power is going to equal 0 plus c. Right? And now I can solve for c, and c is just equal to e, that 2.78 constant. So my general solution, my particular solution is going to be the general solution, but with the replacement of the c value. So this is going to be e to the z equal to p plus e. Good. And if I want to solve explicitly, I'm going to be solving for z. So in order to solve for z, I can take the ln of both sides. And that would translate it to z. And this is my particular solution that passes through that point. Good. All right. I'm going to stop here just to make it a small video, and I will move forward with proportionality problems to see how real-world situations can give rise to differential equations. I'll see you in a minute.